Hi, this is Greg McKee, Product Marketing Manager and Chief Technologist for LabSphere. This video is one in a series of videos on LabSphere's Spectra FT fine-tunable sources. Spectra FT is part of LabSphere's spectral image and sensor calibration and test sources. Today we want to show you our FT2300 fine-tunable wide-angle field of view flat fielding source user interface. You're looking at the main screen right now. I have an Illuminate A spectrum up. The gold line in the plot is the target spectra. The white line in the plot is the characterization file. It's the performance of matching. I'll turn on the spectrometer. And the spectrometer, which is the pink line, is measuring what the spectral radiance output is. You can see there's a very good match between how we optimize that spectrum to match that target and the measurement that we're getting from the internal spectrometer, which is monitor target. On the left here, you can see under characterization, that is the photometric values produced by the target file. So calculating photometric values from the target spectrum. And then the spectrometer readings are used to calculate the photometric values of what's coming through the exit port of the sphere. We have the chromaticity diagram over here, which is monitoring both what the characterization or the target file or target spectrum output is. And there's a second X there, which is what the spectroradiometer is reading. And so if I change the spectrum, you can see that the blue X goes to the spectrum I chose, and the following X, which is the spectrometer, overlays it because that's what it's measuring. This drop-down box here is a series of files that we can load, and our customers can load as many as they want to characterize. And you can see that how well it performs for each one. Our metric for performance, we use an A prime. Please watch that video, which I'll discuss what that metric is. You can turn the spectrometer on and off, which I'm showing here. You can select different spectrums very quickly. You can also choose them manually. Down below, you'll see this, this bar across the bottom. This is the input for each individual LED. These are the individual LEDs. So if I, let's just say if I selected Illuminate E, this shows a good representation of how the instrument covers the full vis near IR from or silicon range from roughly 390 to 1,000 nanometers. I can control the output, and we characterize these systems over the full dynamic range. And so no matter what spectrum you choose, you're getting the full matching over the dynamic range of the system. I can bring this down to 0, for example, and I can select individual LEDs. And so you can play with individual LED input. Go back to Illuminate E, 1855, and I can turn it back up. One more thing I want to share with you on this screen, it's a very user-friendly interface, is the manual levels. And so I can select a specific luminance level that I want to go to. It's let's just choose 15,000 for an example. Use that spectra, and it drives it to 15,000. I told it to go here, and then that's what the spectroradiometer is reading, 15,000. And color matching matrix. We have other levels or other drop-down menus that I want to share with you, and I'm going to do that in another video. Today we want to show you our FT2300 fine-tunable wide-angle field of view flat fielding source and how to load and optimize a source to reproduce a given spectral target. Just to refamiliarize yourself with our system, the gold line is the target spectrum. The white line is how well it's matching. That's the optimization file, which we're going to show you how to produce. And the pink line is a measurement which is done by a spectroradiometer inside the system. So this is the spectroradiance output of the system, and that is showing you the output here on the left. What I wanted to show you today is our solver, and so I'm going to load a new target. So this is the maximum output of our system, and so I'm going to open a target. Let's see if we can find one here. New target. I'm going to choose one that covers the full spectrum of our system, so you have a good idea of what it looks like. So we'll choose this one, 6500K black body, visible near IR. So this is a simple file, literally just two columns, one column of wavelength and one column of relative spectral radiance. We tell the system this column is wavelength, and I tell the system this column is data. It's going to know to use those two columns. There's that 65K black body curve, and so I want to get it under the maximum output of our system, so I'm just going to lower it down. Now the full output will be under the full output of the system. I can put this anywhere underneath it, but I'm just putting it under there and maximizing it that way. I can choose my SI units that I want to use, or my spectral radiance values. I'm just stick with this. I can clear this in on board. We'll save this and give it a name. We'll call it 6500K black body. Sounds good. Okay. Now I'll cover editing targets in the next video. Here I'm just going to go to settings, and you'll see that it's highlighted the one that I just chose. And here's one I did. We're going to do this one right here, and then I'm going to apply it, and I'm going to ask for it to solve. Now you can choose the resolution on how much you want this to solve. So I have it for a typical demo mode here, and so it takes about 2 minutes to go through the process of optimization. So we'll watch it in the beginning, and then we'll cut back. So here we are. We're at 3% of the total output, and it's optimizing at 3% of the total output. Now we're at 0.5% of the total output. And this is going to continue up. And as a user, you can select the resolution of how much you want to optimize. And now we're getting up to 1%. Over on the left here is the target, which is that 65K, that gold line. The white is the spectral matching, and then these are the errors associated with it. So it gives you an idea how well it's spectral matching over the dynamic range of the system. And we'll just let this go, and we'll be done in about 2 minutes. Okay, we're just about done here. I really like how this looks. You can see that we're at 100% of full scale. And so where's that file I just created? These are all temp files that have been created in the past, and you can look at these. There's the one that I just created. I'm going to drive it over here from temporary to this side, current use. If I didn't like it, I can take a file and I can drop it down here and trace it. So if I don't like something, I can just drop it down there. And now I will commit to new files. Back out. And it should be here. There it is. It's 500 body curve. And there we go. So I just created that file. There's the gold and my matching, and I have it over the dynamic range of the system. And you can see the spectrometer catches up here. There we go, how well it matches. Today we want to show you our FT2300 fine-tunable wide-angle field of view flat fielding source user interface and how to create a weighted spectrum. Just a brief overview of the user interface. Here we can select the spectrum that we want to show. We have 3 different scans showing here. The gold scan is our target spectra, which we want to match. The white scan is the summation of our optimization based off these LED inputs to the system. And the pink is the integrated spectroradiometer that's monitoring the spectral radiance output. These are the metrics for photometry based off of the spectral radiance of the target and the spectral radiance measured with the spectroradiometer. And you can see there's a very good match between the two. The spectroradiometer can be turned on and off. And as always with these systems, they're characterized and calibrated over the full dynamic range of the system. What I want to show you today is how do you combine 2 spectrum? For example, what a surface might look like, a reflective surface, and the rendering of that surface when illuminated with a different light source or a light source or spectrum, and then have our FT2300 be able to reproduce that combination of the reflectance and illumination source. So for example, we can pull up a D65 source. That's a standard D65. And for this example, I have a red spectra. Let's say this is just a color standard or a red sign. And I want to know what that is going to look like when illuminated with D65, and then reproduce it with the FT23 spectral radiance flat fielding source. So first we'll go into the solver, which is a window that allows us to create new targets. Here we go, and we can create new targets. We can load targets externally from files that we created or you can create. It's endless how many files that you want to load into the FT2300 or Spectra FT products. But what we want to show you is that I have 2 spectrums already saved, and we talked about the D65 would be the illumination source, and we're going to look at the red spectra. And so what I'm showing here is there's the D65 source, which is in green. The red spectra is in purple, and the white is the combination of the 2. This orange line is the maximum output of this FT2300, so I'm going to increase the level so just under the maximum output of this system, and I'm going to save this, and I'll just, for example, red under D65. Okay, and I commit that. And so what the software is going to do now, it's going to solve for that. Let's see, settings should show here. Red under D65, apply, and solve. And there we go. So we have red under D65, and this normally takes about 2 minutes. Right now it's at 0.1% of max. It's going to go through an iteration of optimizing the LED source, the FT2300, at this power level. And then it will do it again at 0.3%, and it will iteratively go up. And these are settings that the user can set on the resolution of this matching. And then when it's done, we'll have a nice spectral match and reproduction of the source. Okay, this looks pretty good. That only took about 2 minutes. I have it set on pretty high resolution for matching. And you can see that we're getting pretty good metrics here between the target and the solution. You compare the 2. And there it is right here. It's a temporary file right now, and I'm going to move it over to here, current use. apply those changes. And now it's going to go back out here. And we'll go find that right under D65. And there you go. And so that would be the output of the source right now, which is representing the red target illuminated by a D65 source. And you can see how the CRI changes. So if I have, I'm shown the 54.75, and if I just go to the original reflectance factor, it was 56. Today we want to show you our FT2300 fine-tunable wide-angle field of view flat fielding source metric for total in-band radiance matching. As a reminder, the gold line is the target spectra. The white line is the optimization, how well we optimize. This is the output of the source, which is covers the full dynamic range of the source. And the pink line is a spectroradiometer that's inside the sphere monitoring the spectral radiance through the exit port, which is showing you that we have a very good match between the optimization and what it's measuring. So I wanted to talk about this metric, this target versus actual. So the actual is the characterization file, which is the, or the target file, which is the gold line. And the spectrometer reading is what's coming out the sphere. And so the spectral reading is coming through the sphere. And the A prime is what we characterize as a performance for the difference between the two. So let's just pick spectrum, illuminant C. So how well is illuminant C matching to the standard illuminant C? So again, the gold line is illuminant C, which is the characterization, this gold line. And the spectrometer reading, which is the pink line, is what it's measuring. And so the out-of-band radiance is equivalent to 6% of the total radiance within that band. So this is a good metric that allows you to compare different spectrums or new spectrums. You might set a level where, as a user, that you don't want this to exceed 10% or 15% or 5%. And so you can use this as a metric to say, I do have a good total radiance match or total luminance match, or I don't. It can also be used to compare products. LabSphere has several products. We have this fine-tuned source. We also have a series of ultra-tuned sources, which we use that same metric, and you can use that to determine which product is going to be best for your application as far as integrated radiance under the curve. Today we want to show you our FT2300 fine-tunable wide-angle field of view flat field source UI and spectrometer calibration feature. Let me show you how that works. So here I have an illuminant E. The white line, or the gold line, is the illuminant E spectra. The white line is our spectral matching with the FT2300. Metric is showing how well it is. And if I turn on the spectrometer, this is an embedded spectrometer inside the source, which is measuring the spectral radiance through the exit port. Now, this is giving you your metrics of how well is the optimization holding up. So it's important that the spectroradiometer always be calibrated. So how do we do that? With our FT2300, we have a tungsten halogen light source in there, which is a very stable source, which we calibrate this FT2300. We characterize it and for spectral radiance using that halogen source inside the sphere and the spectroradiometer inside the sphere, and a NIST traceable spectral radiance calibration through the port. That spectral radiance calibration is transferred to that tungsten source inside the sphere, and that can be used to recalibrate this spectral monitor, which is the pink line. So let's say that after a month or two, You notice that the spectral radiance monitor is starting to drift down a little bit, so you want to recharacterize that so you get an accurate reading of the spectral radiance coming through the port. We have this feature in our settings, and you can see here we have calibration functions, and this applies to the spectroradiometer. We also have a recharacterization feature, which I will speak about that in a separate video, and hope you join me for that. So here we have a new baseline offset correction. When you operate the FT2300, when you execute the software, it gives you the option to do a baseline correction. That is simply putting the system in dark, or covering the port and running a baseline offset. It's a dark scan, which then corrects any noise in the spectrometer. And then we have a stray light feature, which LabSir provides. We do a stray light correction on our spectroradiometers. This helps get a more accurate reading in the blue, and so it takes out the noise and the calibration from the tungsten halogen lamp in the blue, or the stray light. And so your system comes with a stray light correction factor for that spectrometer that's with your system. And finally, I just want to share that you have this calibrate. And so in this calibration function, you give it a name. It's at date stamped, and you can choose the calibration lamp that's in sphere. So that's a calibration file for the spectral radiance. And then when you execute it, it's going to walk you through the process. It's going to turn on the tungsten halogen light source. It's going to let you know when it's stable, and then it's going to run through the calibration process. And when it's done, now your spectroradiometer has a new calibration factor. And you'd be all set to go. Today we want to show you our FT2300 fine-tunable wide-angle field of view flat fielding source and UI and its recharacterization feature. What I'm showing here is the main user interface. The gold line is the target spectra. The white line is our spectral matching. And when there's an internal spectrometer that's measuring the spectral radiance output, so you can always check if the optimization or the LEDs are behaving as it was when it was optimized at LabSphere or characterized at LabSphere. So you can see that we have multiple spectrums programmed in this system, and the customers or users can reprogram as many spectrum into this as they want. There's no limitations to characterization files that you want to optimize to. And it's optimized over the full dynamic range of the system as well. So let me just, for example, go to an Illuminate E, which is a good spectrum to work with here. So here we have the Illuminate E flat line, and then the gold line is the LED input. These are what each LED is inputting to that spectrum, represented by these LED spectrums below. The gold line is the combination of these LEDs below, and that's over the dynamic range of the system. The spectrometer, once again, is monitoring the spectral radiance output of the system. So let's say after 10,000 hours or so, one of your LEDs, let me turn this up a little bit, one of your LEDs starts to drop. Okay? You're going to see this in your spectral radiance measurement from the spectrometer, which is monitoring the spectral radiance output. Now, of course, it's a little dramatic, but let's say it just drops a little bit. And you're looking at this metric here that as that drops, your metric gets worse, right? The spectral matching. So say after 10,000 hours, you notice that that's happening. What do? You send it back to LabSphere. You do not have to do that. You can recharacterize your system. When we send out a system at a new buy, we do a manufacturer's characterization of the system. We characterize the spectral radiance of the source over its full dynamic range. Then we optimize selected targets, which we provide to you, and then you can add more targets, as many as you want. But if one LED or two LEDs, you see LEDs are starting to decline after 10,000 hours of use, you want to recharacterize it. You don't want to send it back to LabSphere because it might mean that you'll be down for a couple of weeks. So what are your choices? Well, you can send it back to LabSphere, or you can go into the settings here and you have new characterization. This new characterization is an optimization of the system, just like we do here at our facility. The system has a built-in mistraceable spectral radiance calibration tied to a tungsten halogen source, which is in the source, and this spectroradiometer, which is calibrated for spectral radiance responsivity, which you have the feature to recalibrate that spectroradiometer anytime. But when you run the recharacterization, it uses that spectroradiometer to re-optimize this system over its full dynamic range. It's as simply as setting it up before you go home at night and come in the morning, and it's done. And then you're all set. Your system has been recharacterized. Your LEDs, your optimization program has optimized for the LEDs on how they're performing at this date that you did your recharacterization, and you're good to go. The system does not have to come back to LabSphere.
I hope this was helpful. For more videos on Spectra FT and other LabSphere products, visit us at www.labsphere.com.